right? So what we will do is we will revisit some of these again whenever required, but let's move on to convex functions now, right? Before that, okay, so I have to give one more example here, right? Example of a convex set. So example, set of all x such that A transpose x is less than or equal to B. What is this set? What is this called? Remember, what is A transpose x equal to B? Set of all x such that A transpose x equal to B. What is that? Hyperplane, right? So what is A transpose x less than or equal to B? Huh? It's all the points on the hyperplane and below the hyperplane, right? It's called a half space. Did I mention that before? No? Okay, so this is called a half space. Okay. Well, why is it called a half space? So if you have this, it's all the space below that hyperplane. This is an everlasting hyperplane. So, well, by definition, hyperplane means everlasting. Okay. So it's half the space, right? So below it. Do you agree? Yeah. That's why it's called half space. So is this a convex set? Well, intuitively you see, you take 2 points here and maybe here. I take all the points in between. Of course, it's there, right? So is this a convex set? Yes. So how do you prove that? You take 2 points, right? Let you take 2 points. Maybe I'll call it as x and y belongs to. I'll call this as h, right? Then I have to check if lambda x plus 1 minus lambda y, whether this belongs to the set or not, right? So how do I verify? I have to ensure that A transpose times this convex combination is less than or equal to B. If I show that, then it belongs to. That's trivial, right? So lambda A transpose x plus 1 minus lambda A transpose y, but this is less than or equal to A transpose x is less than B. A transpose y is also less than or equal to B. You will get B, right? So A transpose times the new point is less than or equal to B. Therefore, this implies lambda x plus 1 minus lambda y belongs to C. Sorry, belongs to H. Right? So that proves that half space is a convex set. Okay. Now, another small result. If I take 2 convex sets, right? Let C1, C2 subset of Rn be convex sets. Okay, I have 2 convex sets. Then what can you say about C1 intersection C2? Of course, this is a subset of Rn. Is this a convex set? Huh? Let's verify, right? So how do you prove this? It's easy. You take 2 points. Let x, y belongs to C1 intersection C2, right? I have to show that convex combination of these 2 points also belong to the intersection. So what do you mean by that? It should belong to both S1 and C1 and C2, right? That's what I have to prove. So since xy belongs to both, it should belong to C1 and it should also belong to C2, right? So this implies xy belongs to C1 and xy belongs to C2. What does this mean? See, remember C1 is a convex set, right? So convex combination should also belong, right? Lambda x plus 1 minus lambda y belongs to C1 and lambda x plus 1 minus lambda y also belong to C2, right? Because both are convex sets.